In this video, I want to go over rice examples and how we incorporate rice tables with equilibrium. So the very first thing you have to be able to do when you're writing a rice chart is to write your balanced reaction. So in my reaction, I have SO2, O2, and they're being put together to react to form SO3. So we're going to start off by writing our reaction there. So I start with SO2 plus O2 yield to SO3. And again, we're going to use double arrows here because we're dealing with equilibrium. So this is our reaction. We have to make sure that it's balanced. So in order to balance this reaction, I'll put a 2 in front of the SO2 and a 2 also in front of the SO3. So we have the first part of our rice chart, which is our reaction. After that, I then plug in my initial values. So you have to be careful and look for keywords in these problems whenever you're plugging in initial values. So you're looking for keywords like introduced, initial, or at instant of mixing. Those keywords tell you that those are initial values, and I always put the initial values in the I line of my rice chart. Now, if you remember from stoichiometry, what we would put in this I line was moles. When we're dealing with equilibrium, if we're dealing with Kc, we're going to be putting in concentrations in our rice chart. And if we're dealing with Kp, we're going to be putting pressure in the form of atmospheres in our rice chart. So it can be used here as well. We're still looking at the stoichiometry, and that will come into play in the C line. And then the E line will show us our equilibrium values. Now remember, equilibrium values are the only things that I can plug into my K expressions. So let's read this question and kind of fill out our rice chart and figure out what we need to look for. So we have 6 moles of SO2. Now, since we're looking for KEQ, which is the same thing as KC, we need to put molarities or concentrations into our rice chart. So we have to figure out not what this is in moles, but what this is in molarity. And we know that molarity is equal to moles over liters. They were really nice to us and they told us 1 liter. So however many moles is there, it will be equal to my molarity as well. So our SO2 is starting at 6 molar. Our O2 is 4 divided by 1, which is 4 molar. And because it doesn't give us an initial value of SO3, then we just put that as 0. Now we look for our C line, what's happening there. Well, since these are reacting, they are going to subtract by some number. And since this is being produced, it's going to add by some number or increase by some number. And we don't really know that number. It's not like stoichiometry where we have to figure out where those are, who's limited reactant, and anything like that. We don't have to do that here. Instead, they're going to change by some number that is equivalent to the proportion that you have. So you see how I have a 2 to 1 to 2 relationship. So what we're going to call this line here is minus 2x. X is the number that it's changing by. 2 because of the coefficient. So oxygen will just be minus x, 1x, because there's a 1 coefficient. And this will be adding by 2x because there's a 2 coefficient there. Now, if I combine my initial and my change, I will get my equilibrium expression. So all I have to do is combine these two together. So equilibrium for SO2 will be 6 minus 2x. For O2, it'll be 4 minus x. And for SO3, it will be 2x. Now, the whole point of this question is to calculate K. So let's just kind of step aside right here and figure out what my K expression would be. So I'll write my K expression. Remember, it's products raised to the coefficient over reactants raised to their coefficient. So my products are SO3 and I'm going to raise it to that second power because the 2 coefficient over SO2 raised to the second power times O2. So this is my equilibrium expression. So in order to figure out the value of my K, I need to plug equilibrium concentrations in right here. Well, the problem is, I know that there's some expression according to X, but I don't know numerically what those values are. So there has to be some piece of information in this problem to tell me what X could be, or to help me solve for X. So I keep reading. And here's our keyword here. At equilibrium, the vessel contains 4 moles of SO3. So what that means is that at equilibrium, this value 2x is equal to 4 molar. Now that I have that expression, I can solve for x here. If 2x is equal to 4 molar, then x is equal to 2. Well, now, if I know what x is, I can figure out what the other values here are. All I have to do is plug this x, plug 2 in right here. So 6 minus 2 times 2 is equal to 2 molar. 4 minus 2 is equal to 2 molar as well. So you see how I'm using information from this problem. The keyword here is equilibrium values to solve for x, and then I'm able to solve for all of the equilibrium values for each of these things here. Now what I'm going to do is I'm going to take these equilibrium values and plug them into my expression. So for this SO3, I'm going to plug in 4 molar. For O2, I'm going to plug in 2 molar. And for SO2, I'm going to also plug in 2 molar. Once I do so, I solve for K. So remember, it's 4 squared over 2 squared times 2. That ends up giving you a K value that is equal to 2. So this is one way they can ask these equilibrium questions where you're trying to incorporate Rice charts. You see how they give me initial values, some piece of equilibrium value, and you're solving for K. Let's move on to the second example to figure out another way that they can ask a Rice table problem dealing with equilibrium. So let me scroll down here. We'll look at number 2. I'm going to give myself some space. All right. So for number 2, we have the equilibrium constant to begin with. So we know that our K value is equal to 85. So we might have to use this a little bit later on. It says, if a mixture is prepared where the initial, that's a keyword, concentration of sulfur dioxide and nitrogen dioxide is 2 moles over liter, that's the same thing as saying molarity, calculate the equilibrium concentrations. So we want to find equilibrium concentrations of nitrogen monoxide and nitrogen dioxide. So in this problem, we have the K value given to us, and we're trying to find the equilibrium values. So the very first thing I do again is set up on my Rice chart. So I have R already. For my I value, it tells me sulfur dioxide and nitrogen dioxide are 2 molar. So I'm going to plug in 2 molar here and 2 molar here. Because they don't give us any information about NO and SO3, those are both 0. Now let's fill out my C line. It's all according to the stoichiometry. So this is going to subtract by X because it's a reactant. This is going to also subtract by X. And this my products, because they're being made, they're both going to be adding x. Now, if I had a coefficient for any of those, then I would put my coefficient there as a multiple of x. Now it's time to write our e-line. So this one is 2 minus x, 2 minus x, and both of these are x. So now let's leave this all to the side and let's write our k expression. So our k expression, I'm going to write to the left here, is equal to NO times SO3 over SO2 times NO2. So that's my equilibrium expression. Now what I also know is that K has a value. So what I'm going to do here is I'm going to plug in these equilibrium expressions here. So 2 minus x for both of these and x for both of these. And I'm going to set it equal to my k. Well, since I know my k value for this one, I can use this expression to solve for x. And if I can use my expression to solve for x, then I can figure out what these equilibrium values are. So here we go. Let's plug all this stuff in. So k, which is 85, is equal to 2 minus x times 2 minus x. That will go on the bottom, right? Because it's products over reactants. And x will go on the top, right? So x times x, isn't that just simplified by x squared? And 2 minus x times 2 minus x, well, that's simplified to 2 minus x squared. Now this is where your algebra skills come in handy, okay? How do I solve for this? What do I need to do for my order of operations? Well, the very first thing I need to do is get rid of these squares. So I'm going to square both sides. And when I do, it gets rid of the squared portion of x and 2 minus x. But make sure you take the square root of both sides. So the square root of 85 is equal to 9.2, and that's equal to x over 2 minus x. Now we have a nice and neat proportion. So we just solve using proportions. So here we go. 9.2 times 2 is equal to 18.4 minus 9.2 times negative x, which is where that minus is. So that we have minus 9.2x is equal to x. Now we have to get our things on the same side, like terms. That's an x right there, I'm sorry. So 9.2x right here. We have to combine like terms. So I'm going to add 9.2x on both sides. And when I do so, this is essentially 1x, right? So both of these combine to make 10.2x. And you set that equal to, that's gone away, 18.4. Now we've simplified it enough to where all I have to do is divide by 10.2 on both sides. So I divided by 10.2 on both sides, and you end up getting x to equal to 1.8. So this is where your algebra skills really come in handy, okay? Again, what I did is I plugged in these values into my expression, and I solved for x using algebra. Now, you might say, ooh, all right, I'm done. I got my answer. I know what x is. Well, this isn't just math class. We have to apply x. We have to apply the math here. So what does this mean? Well, all I'm going to do is take that x value and plug it into my equilibrium expressions here. So this x means that this concentration of SO3 at equilibrium is 1.8 molar. Same thing for NO. that equilibrium concentration is 1.8 molar. Now for these, since they're 2 minus x, I say 2 minus 1.8, and that gives me 0.2 molar for its concentration and 0.2 molar for its concentration as well. So now I've answered my question and I know my equilibrium concentrations for each of my species there. So this is kind of working backwards from number one. Number one, we were trying to find K. We were given some piece of information about equilibrium concentration. For this one, number two, we are given K and we're trying to find those equilibrium concentrations. So I want to show you one more example of how we can see these rice charts applied in equilibrium. I'm actually going to scoot this back up. All right, so here we go. For this question here, again, we're trying to find the K value. So we're going to have to set up our rice chart to solve for my K values. So we're going to need to know those equilibrium values. Now, it gives us a little bit different piece of information. It tells us a percentage that's decomposing. So I'm going to show you where this comes into play. So let's first write our reaction. So R, phosphorus pentachloride, so that's PCl5, goes to phosphorus trichloride, so that's PCl3, plus chlorine gas, plus Cl2. All right, let's fill out our chart. So initial values, the only initial value that it gives me is of phosphorus pentachloride, and it says 1 molar. So 1 molar goes here. So these products here are 0. For C, this is going to decrease by X, use its coefficient, plus X, and plus X. So now, if I write my equilibrium expressions, it's 1 minus X, X, and X. So let's go back to this 13.9%. So what it's saying is 13.9% of this phosphorus decomposes. Whenever it's telling you a percentage that is reacting, a percentage that is decomposing, a percentage that is disappearing, that is code word for your X value. So that is your code word for what's changing. Any percentage talked about is your code for change. And it has to say decompose, it has to say disappear, it has to say react, something like that. So what I'm going to do is I'm going to take 13.9% of 1 molar. Now remember, when you take a percentage of something, I can't say 13.9 times 1. I have to put that in decimal form. So it's going to be 0.139 times 1 is going to tell me what X is. So X ends up being 0.139. So now all I'm going to do is use that value to solve for these equilibrium values. So this ends up being 0.139 molar. Same thing here, 0.139 molar. And 1 minus 0.139 gives me 0.861. Now, this isn't what the question is asking. It doesn't want to know what our equilibrium values are. It wants to know what our equilibrium constant is. So let's write our equilibrium expression. So I'm going to write it right up here. K is equal to PCl3 times Cl2 over PCl5. Always write your equilibrium expression first without plugging in any numbers because they love to give you credit for that. Okay? So don't plug in your numbers, write your expression first. And then you can start plugging in numbers because you'll almost always be guaranteed a point there. Um, let's see. Now we're going to plug in our values. And so we get 0.139 times 0.139. Is it okay if I simplify it to squared? Hopefully that makes sense to you. Over 0.861. So when I solve for that value, you end up getting 0.0224 for your K value. Now again, K doesn't have any units. It's like a little jaybird, so I leave it alone like that. So I hope this was a good way to kind of show you how to work these rice charts. You will be working them tons. In this unit, when we're talking about KSP after Thanksgiving break, whenever we're doing acid base, you're going to be working these rice tables a lot. So it's really important to pick out keywords from there and be able to set up your chart to organize your information.